let's get started. First of all, I am going to honor the walkout on Thursday, so there won't be lecture or office hours on Thursday. If you have questions about the material, post them to the discussion board, and I'll try to turn stuff around quickly on the discussion board. We are making good progress through the book, so things are still on schedule even without that lecture, so I'm not worried about that too much. By way of explanation, I'm dressed almost like a grown-up today. One of the things that makes statistics so fun, the thing that makes statistics the most fun for me, is that any problem, any field that has data, there's a chance for a statistician to do something useful. And by virtue of having UC Berkeley letterhead, very often if I tap somebody on the shoulder who's working on something really cool, they will take the time to explain it to me, which is really, really nice. I got asked last week to address this group of people. It's they're government officials, people, I guess, from power companies and private consultants who are studying how many birds get killed by the wind turbines in Altamont Pass, so the wind power generation in Altamont. So, as you know, wind energy is nice, renewable, clean, et cetera, but birds hit the turbines and get killed. And some environmentalists are in an uproar over the number of birds that get killed. And one question is, well, how many birds do get killed? And it turns out to be quite a complicated statistical problem to estimate, because you walk out there and try to count the birds that you find on the ground. Well, it depends on how long it's been since the last time you counted. And some birds die of sort of natural causes. Some hit the turbines and die. Some hit the turbines, are injured, get somewhere else, and then die. After they die and hit the ground, scavengers come and eat some of them, right? If they land in tall grass, you're not going to find them. Smaller birds and dull-colored birds are less likely to be found than brighter colored, birds that have high contrast in the environment are larger. There's like all kinds of complication just in figuring out what's going on. And people have made up various models for this stuff. Well, it turns out that it's also related to other problems I've worked on, like earthquake catalogs. So when people try to count how many earthquakes there are in a given region, the smaller the earthquake, the bigger the chance that you're not going to see it, right? That somehow it won't be recorded by your network of instruments, or it won't be recorded reliably enough to be able to figure out where it is, or something like that. Similarly, there are problems that come up in astrophysics that are related to this, that sort of the further away and the dimmer objects are, the less likely you'll pick them up in a sky survey. There's all kinds of problems related to how do you figure out how much light gets blocked by the dust in a galaxy or dust between galaxies, and figuring out how many stars are there of a certain magnitude a certain distance away. And this also gets tied into stuff I've worked on election auditing, which I've been doing a lot of in the last few years. We're trying to figure out, anytime you have an election, there's going to be an error in how the votes are counted, right? There's no system for counting votes that's perfect. People are especially suspicious of electronic voting machines, and rightly so. But regardless, however it is that you count votes, you're going to make some mistakes. Are there enough of those mistakes to change the outcome of the election? Right? Well, it turns out that errors in counting votes are relatively rare, just like there are relatively few birds get hit, right? The counts that people get are mostly zero, but occasionally large. Similarly, election vote counting errors are mostly zero, but occasionally large. And when you look out at the night sky is mostly black and occasionally very bright, where there's a star or a galaxy or something like that. So all these problems share some common structure, and there's an opportunity to do some statistics and learn some cool stuff from other people, which is what makes this fun for me. So that's why I'm dressed up, relatively speaking. Okay, we were talking about counting things, and we had talked about combinations and permutations. And I want to talk about some connections between them and then do a bunch of example problems involving poker hands. A lot of the theory of probability originated with games of chance. It originated with gambling and figuring out how should you bet. How should you bet in order to maximize the amount of money you walk away with. And games like cards are particularly amenable to dealing with probabilistically, because the assumption that the cards are well mixed, that the hand that you get is like a random sample, can in some sense be verified. If somebody isn't cheating, right, if somebody isn't stacking the deck in some way, if they really do shuffle it, 8, 10, 12 times, the cards ought to be pretty well mixed together, right? Just like taking a big pot of soup and stirring up the soup really, really well. So that kind of mixing together of things so that all possibilities are equally likely is crucial to being able to figure out what the probability of a hand is. And it's an assumption that is justified in many real-world situations, but certainly not in all. And it's an assumption that is made in many cases where it actually doesn't apply. It's not a good assumption. So we want to be really careful in distinguishing between things that are haphazard or sort of unpredictable from things that are actually random in a well-defined sense. We'll be getting there maybe later this lecture, certainly next time we get together. But meanwhile, we're talking about counting stuff. Are there any questions right now? Okay. So let's talk about, we were talking about permutations, which are the NPK is the number of ways there are of taking k of n things and putting them into some order. And you can think of that as a two-step process. First, you pick k of n things, and then you put those things in one of the possible orders. So how many orders are there that you can put k particular objects in? If you can distinguish between these objects, how many ways are there of ordering them? K things. A lot if k is big. Yeah, no. So we've got chalk, maybe, maybe not. I was counting on using chalk today. Goodness. I might be stymied. Okay, so we have k things. K places. How many orders can we put these things in? Well, we get to pick which one goes first. And having done that, we get to pick which one goes second from the remaining ones. And having done that, we get to pick which one goes third from the remaining ones. There's k choices for what's first, k minus 1 for what's second, k minus 2 for what's third, et cetera, on down to 1, right? And this, so by the fundamental rule of counting, since the number of choices I have at the second stage doesn't depend on what I picked at the first stage, it's always the same. The number of choices I have at the third stage doesn't depend on what I picked the first or second stage, et cetera. The total number of ways there are of putting k things into an order is k times k minus 1 times k minus 2, et cetera, which is k factorial. So there's k factorial ways of putting these things into some particular order. So we've now just thought of taking some larger set of n things, from the n, picking k, and then taking those k and putting them in some particular order. Right? And if we do that sort of all at once, if we're just going to take k of the n and put them in some order, what are our possibilities? Well, we have n choices for the thing that goes first, n minus 1 for the thing that goes second, et cetera. And we keep doing that until we have k objects lined up in a row. So the number of choices we have at the first stage is n. Having picked the first one, we have n minus 1 choices for the second, et cetera. We're doing k things in all. So these factors would look like n times n minus 1 times n minus 2, so forth, times n minus k plus 1. What's the plus 1 doing there? Is it right? Have I written down n numbers? Or have I written down k numbers? You guys need to caffeinate more before class. Should we do a special case? Okay, let's suppose that n is 10, and we're trying to put 7 of the 10 things into some order. Okay, so let's take the special case. Okay, so we would have 10 choices for the first, 9 for the second, 8 for the third, 7, 6, 5, 4. Is that 7 things? Okay, what's the last term? Yep, which is 10 minus 7 is 3 plus 1 is 4. Okay, so there are k terms in this list, n minus 1 on down to n minus k plus 1. Okay, that's why it ends there. All right. Okay, so we just thought about doing this in one particular way of framing the problem, which is we're going to end up with k things. We have n choices for the first, n minus 1 for the second, on down to n minus k plus 1 for the kth of those k things. And by the fundamental rule of counting, since it doesn't matter, the number of choices you have available to you at any step doesn't depend on what you picked in the previous steps. The total number of ways there are of picking k of n things is n times n minus 1 times n minus 2, etc. So that looks like n minus 1 times n minus k plus 1. And this has a symbol, which is npk. Okay, that's a definition. We'll use three horizontal bars to indicate that this is a definition. And it turns out that we can relate that number, we can express that number in terms of factorials as well. Okay? If we had continued this product, by the way, these are not division signs. These are places. Okay? I'm not intending to divide anything here. These are just locations. If we continued n times n minus 1, n minus 2, n minus k plus 1, n minus k minus 1, n minus k minus 2, etc., on down to 1, then this would be n factorial, right? So instead of having n factorial, we've terminated this product at n minus k plus 1. Well, what do the remaining terms look like that aren't here? It's n minus k times n minus k minus 1 times n minus k minus 2, etc., right? So the sort of the missing terms that would make that n factorial, this thing that we're looking at, I'll go over here. So n times n minus 1 times n minus 2, n minus k plus 1 is actually equal to n times n minus 1 times n minus 2 times n minus k plus 1 times n minus k times n minus k minus 1 times 1, right? If we divide off n minus k minus 1 times 1. Right? So that would cancel that, etc. Those would all cancel. And it would leave us with what we have before. Okay, but this product in the numerator is n factorial. And the product in the denominator, n minus k minus 1, etc., is n minus k factorial. Okay. So this number, npk, is equal to n factorial over n minus k factorial. Same thing, just expressed a different way. So far, so good? Okay. Well, we also said that we could get k of n things into some order by first picking the set of k things without regard to their order, and then putting them in some order, right? So instead of instead of, if the 10 objects were, I'm going to get rid of the screen for the moment. I think it's just in the way. And the question is, if I use a different source, will this go blank? It will. All right, so let's suppose that my 10 objects are A, B, C, D, E, F, G, H. Is that 10? Is that 10? Wish I had chalk. Aha. Fragment. Okay, so the way we just conceptualized this process was, I'm going to pick one of these 10 things to be first. Let's say that it's A. And I'm going to pick one of these things to be second. Let's say it's F. And I'm going to pick one to be third. Let's say it's D. And then I'm going to pick B. And then I'm going to pick H. And then I'm going to pick J. And then I'm going to pick C. Okay, so that's one particular ordering of 7 of these 10 things. That leads kind of directly to this notion of NPK. There's a different way we could get there. We could first say, oh, I'm going to pick the set A, B, C, D, F, H, J. Okay, and then I'm going to put these 7 things into some particular order, and that's an example of an order I could put those 7 things into. So far, so good? All right. So the number of ways there are of putting 7 of 10 things into some order is the number of ways there are of picking 7 of 10 things and then putting those 7 of 10 things into some particular order. Right? This 2-stage process gives the same number of results as the 1-stage process. Yep. So how many ways are there of putting a set of 7 things into some order? We've been given this set now. We picked 7 from the 10, and now we want to put these into some particular order. Okay, so there's 7 factorial ways of ordering these things. I could put the A first. Having put the A first, I have 6 choices. I have 7 choices for what to put first. Might be the A. Having picked that, I have 6 choices for what to put second. Might be the F. Having done that, I have 5 choices for what to put third. Might be the D, right, et cetera. Okay, that would lead to that particular permutation. So because this 2-stage process is going to lead to the same number of sequences of 7 of 10 things, what we know is that the number of sets of 7 of 10 things times 7 factorial is equal to the number of permutations. Right? So if we first pick a set and then put it in some order, we're going to end up getting all sequences of 7 things that way eventually. So we know that this last number is equal to 10p7, which is, okay, time for the other chalk, which is equal to 10 factorial over right? We know that that's equal to that. So the number of sets of 7 of 10 things must be this divided by 7 factorial. Okay? So what we've got now is that the number of sets of 7 of 10 things is equal to is equal to 10p7 divided by 7 factorial, which is equal to 10 factorial over 3 factorial times 7 factorial. Okay, and in general, this reasoning holds, and the number of sets of k of n things is going to be npk over k factorial, which is n factorial over k factorial times n minus k factorial. And we give this a symbol, which is n choose k. Right? That's the number of combinations of n things taken k at a time, the number of subsets of size k taken from a population of size n. All right, let's do some thinking. If I don't care how big the subsets are, how many subsets of n things are there in all, without regard to how big the subsets are? Right, so here I have my n objects, A, B, C, etc. One subset is the trivial subset, the empty set, right? No set with no elements. That's a subset of every set. So that's a subset of this particular set. Okay? Another subset is the whole thing, A, B, C, etc. I'm going to change the symbols here just so that we don't have to think about an infinite number and we have a definite number. Let's call this A1, A2, etc. on up to AN. So there's n objects in all. That's our set. That's supposed to be a curly brace. Okay, so there's one. Here's another subset. Okay, here's another subset. Here's another subset. Here's another subset. Right? There's a whole lot of different subsets we can make. How many are there in all? 2 to the n. Okay. Good answer. I like that answer. Where is that answer coming from? Let's consider these objects to be labeled in some order, okay, like they are there, A1, A2, A3. So they're enumerated in some particular order. We can think of making a subset as a sequence of trials. So what happens at the first stage is we decide, is object A1 going to be in the subset? Okay? And so this is stage 1 where we're figuring out, is A1 in the subset? And we might have yes, no. Okay? At stage 2, we figure out, is A2 in the subset? Okay? And again, this branches to yes, no, right, et cetera. And at every stage, we're deciding whether the next element is going to be in the subset or not. When we get to the bottom of this at stage n, how many leaves is this upside down tree going to have? Well, we have a sequence of trials. There's 2 possibilities for the outcome of each trial, no matter what happened at the previous stage, right? No matter whether A1 is in the subset or not, you have 2 choices. Do you include A2 or do you not include A2? Whether A1 and A2 are in the subset or not, do you include A3 or do you not include A3? So when you get down to the bottom, you've got, by the fundamental rule of counting, 2 times 2 times 2 times 2 times so forth, 2 equals 2 to the n leaves on that tree. Each leaf on that tree corresponds to a subset of A1 through AN. You know, every time you go to the left, you've included an element. Every time you go to the right, you've excluded that element at that level. Is this clear? Okay, so another way to think about it is that you've got sort of an n-digit binary number where you could write, you know, 0, 1, 1, 0, 0, 0, 1, right, et cetera. So this would be, 0 would mean exclude A1, include A2, include A3, exclude, 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 include AN, right? It's like a, so this would be a way of coding a particular subset of this that would have 3 elements, A2, A3, and AN. Well, how many strings like that are there? Well, you have 2 choices for each bit, right? The first one can be a 0, 1, second one can be a 0, 1, third can be a 0, 1, on to the nth can be a 0 or a 1. So there's 2 to the n possibilities. Same reasoning. Okay? How does this connect to n choose k? Well, there's one subset with no elements, right? Okay. So that's, of n objects, how many ways are there of picking no elements at all? That would be n choose 0, right? So n choose 0 ought to be 1, because there's only one subset of size 0 taken from n things, namely the empty set. Oh, is that true? Well, n factorial, k factorial, what's 0 factorial? 1 by definition. That's a definition. And n minus 0 factorial is n factorial. So we have n factorial over 1 times n factorial, which is 1. Right? So this works out to give us the number of subsets of size 0 that there are. Correctly gives them. Well, how many subsets are there of size 1? Well, I could take the first element or the second element or the third element or et cetera on up to the nth element. So there should be n possible subsets of size 1. Right? Please say yes. Okay, so what happens if we plug in, look at n choose 1? What do we get? Well, n factorial over 1 factorial. 1 factorial is 1. N minus 1 factorial. What happens when you take n factorial divided by n minus 1 factorial? N factorial is n times n minus 1, n minus 2, n minus 3, etc. N minus 1 factorial is n minus 1, n minus 2, n minus 3, etc. So all the terms cancel except the first term, which is n. Right? So that cancels that, et cetera, and it just leaves n. Yes? Okay, so this agrees with the notion that there are exactly n subsets of size 1 taken from this. You can pick the first, the second, the third. All right, let's think about how to exploit some symmetries here. How many subsets of size n are there taken from a collection of n things? How many ways are there of picking n of these n things? Just one. You've got to take them all, right? You don't have any choice. There's only one way to do that. So n choose n ought to be 1 as well. Well, all that's happened, the difference between n choose n and n choose 0 is that we flop these terms. N choose 0 gives a 0 factorial and an n minus 0 factorial, which is n factorial. So we get 0 factorial and n factorial. N choose n gives us n factorial and 0 factorial. Same two terms in the opposite order. Product's the same. The ratio's the same. It's still 1. Okay? In general, if I take k and change k to n minus k, what happens to this? Numerically, it's equal. All I've done is change the order of these two terms, because if I take k and take it to n minus k, then what happens to n minus k? N minus k goes to n minus k, which is k. So n choose k is identically equal to n choose n minus k. So this is a little, let's start making a collection of facts over here. Okay, n choose 0 equals n choose n equals 1. N choose k equals n choose n minus k. Those are two little facts we've just discovered. Well, heuristically, why does it make sense for n choose k to be equal to n choose n minus k? Well, picking one element, let me picking one element to be in our subset is the same as picking n minus 1 elements not to be in our subset. Right? You can think of specifying a set or specifying the complement of the set. Right? Picking 2 things to be in the set is completely equivalent to picking n minus 2 things not to be in the set. That's what this is expressing. Picking k things to be in your subset is equivalent to picking n minus k things not to be in your subset. There's the same number of ways of doing those 2 things. They're equivalent. All right. 2 to the n is the total number of subsets that there are. So we can, remember we have this strategy for counting things that consists of take something really big, divide it up into pieces that don't overlap, count what's in the pieces and add the results, and that tells you how many there were in the big thing in the first place. Okay, so if I pose to you the question, what's the sum from k equals 0 to n of n choose k? So that's this sum from k equals 0 to n of n factorial over k factorial n minus k factorial. What's that number? Well, when k is 0, this is the number of subsets of n things that have no elements. When k is 1, this is the number of subsets of size 1 taken from n things. When k is 2, it's the number of subsets of size 2 taken from those things. When k is n, it's the number of subsets of size n taken from those things. So all the subsets, all 2 to the n, can be broken into a bunch of disjoint groups. There are all the subsets of size 0, all the subsets of size 1, all the subsets of size 2, et cetera, on up to all the subsets of size n. So what this is all the subsets of all the different sizes. It's counting them, right? So this answer is 2 to the n. We've partitioned the collection of all subsets into n plus 1 groups. The subsets of size 0, 1, 2, 3, on up to the subsets of size n. There's n plus 1 of those groups in all because we're including the subsets of size 0. This makes sense to everybody so far? Kind of? Getting abstract? Let's do a simple example just to try to make this a little bit more concrete. And then go on and do some card hands. All right. The number of things I'm going to end up with, the number of subsets I'm going to end up with is going to get pretty big pretty quickly if I let n be very big, right? So let's maybe make n 3. Okay. So let's say we have the original set A, B, C, and we want to write down all the subsets there are of that. Okay, and we're going to divide it into subsets of size k, where k is going to go 0, 1, 2, 3. Okay, those are the possible sizes of subsets. So for k equals 0, we only have one subset, the empty set. For k equals 1, so this is, excuse me, 3 choose 0 equals 1, right? That's what we're just calculated. We've enumerated it. There's only one thing there. It all matches. K equals 1, we have three possibilities. We have this subset, we have this subset, and we have this subset. That's 3 choose 1, which is 3. How about instead of 1? Okay, so we've got the subsets of size 0, the subsets of size 1. How about the subsets of size 2? Is this in the way? Well, now we've got this idea that, remember, n choose k is the same as n choose n minus k. We have the subset that leaves A out, the subset that leaves B out, and the subset that leaves C out, right? Is another way to think of these. So one of these subsets is B, C. One of them is A, C. And one of them is A, B. 3 choose 2 equals 3 choose 1 equals 3. Those. And then for k equal 3, we only have one choice, all of them. And that's 3 choose 3 equals 3 choose n minus 3 equals 1. So indeed, we have 1, 2, 3, 4, 5, 6, 7, 8. 2 cubed equals 8 possible subsets. So 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3 is equal to 8. That's all we're doing. We're dividing this collection of subsets into those subsets that have no members, those subsets that have 1, those subsets that have 2, and that subset that has 3. So far, so good? You can say no. Questions? All right, why don't we take like 90-second break, and then we'll do all the standard poker hands, giving you an advantage on the homework over those people who didn't show up today, unless they watched the broadcast. It's been pointed out to me that there is chalk over there, so when I was in grad school, there's this guy who thought that all the really brilliant people were absent-minded, so he used to practice getting off the stairs on the wrong floor. Okay, poker. Cards. People play cards? Who here has never touched a deck of cards? Anyone? Okay, so you've all at least seen a deck. I actually meant to bring a deck with me today, but I left it at home. All right, there's 52 cards in the deck. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King in each of 4 suits, spades, hearts, diamonds, and clubs. We are going to talk about being dealt 5 cards for the sake of argument, and look at all the different kinds of poker hands you can get and count how many ways you can get them. Okay? So one of the important rules in this class, if not in life, is that if you have a hand that can sort of be counted in 2 different ways, it counts as the higher one. So for instance, if I have a hand that is, say, the ace of spades, ace of hearts, ace of diamonds, and the ace of clubs, and the 2 of clubs, okay, there's a particular hand of cards. Okay? It could count as an ace, but it doesn't, because it could also count as a pair of aces, which would beat it. But it doesn't count as a pair of aces because it could count as 3 aces, which would beat that. It doesn't count as 3 of a kind because it also counts as 4 aces, which would beat any of those. Okay, so it counts as the highest thing it can possibly count as. So this is 4 of a kind. All right? Now, where people get bogged down in this is not over this kind of hand, but is over something like the difference between a flush and a royal flush. All right, so do people know what a flush is? It's 5 cards of the same suit. So an example of a flush is, say, ace of spades, 2 of spades, 5 of spades, 7 of spades, 8 of spades. Okay, there's 5 cards, they're all spades. That's a flush. Okay? Now, the following, ace of spades, 2 of spades, 3 of spades, 4 of spades, 5 of spades, that's also a flush, but the 5 cards are all in a row. This is a straight flush. A straight flush beats a flush. So this is not a flush. It's a better hand than a flush. It's a straight flush. Okay? So when you're counting flushes, you need to subtract the straight flushes, right? Don't count the straight flushes. They're a different hand. Okay? All right. So what are the basic kinds of things you can have? You can have nothing, right? In which case your hand is just whatever the highest card in the hand is. So an example of like a king-high hand would be you have the king of spades, the 2 of diamonds, the 4 of clubs, the 5 of clubs, and let's make it the 10 of hearts. You don't have to have one of everything. Let's make it the 10 of spades, because you don't have to have one of anything. Okay, so here you have 5 cards. They're not all the same suit, so there's no flush. They're not all in a row, so they're not a straight. You have no pair of anything, so you don't have 2 of a kind, 3 of a kind, 4 of a kind, or something else. All you got is a king. This is an example of a king-high hand. Okay, this is king-high. Okay? Now, what's the next kind of thing you could have? Well, you could have a pair of something. So you might have king of spades, king of diamonds, 2 of diamonds, 4 of clubs, 5 of clubs. Okay, that's one pair of kings. All right? They're not all the same suit. They can't be because you have a pair of something, right? There aren't 2 kings of spades. There's only one. They're not all in a row. They can't be because you've got a pair of something, so they're not a straight. They're not a straight. They're not a flush. You've got 2 of a kind, but no more than 2 of a kind, right? If the third one of these were king, you'd have 3 of a kind instead of 2 of a kind. That would beat it. It's a different hand. Okay? So that's a pair. Should have just left that up, but I didn't. Okay, what else can we have? We could have king of spades, king of diamonds, king of hearts, 2 of clubs, 4 of diamonds. Okay, that's 3 of a kind. 3 of a kind. I could have 4 of a kind. I could have a full house. Whoops. Okay, a full house is 3 of one kind and 2 of another kind. Okay. Sorry?
Sorry, that beats
No, it doesn't beat 4 of a kind. These are not in any order yet. We'll figure out what order they ought to be in. We're actually going to figure it out. Okay, so that's a full house. Okay, what ought to be the rule for what beats what? Yeah, whatever is easier to get ought to lose, right? Whatever's harder to get ought to win. Whatever there's fewer ways of getting should be the higher hand. Okay, so that's what we're going to figure out why the hands are in the order that they're in. Okay, we could get 2 pair. So that would be king of spades, king of hearts, 2 of clubs, 2 of spades, 5 of spades. So that's 2 pair. Okay, notice a full house is not 2 pair, right? Because it's 2 pair and then some. Right? It's going to be harder to get. All right, what else do we have? We've got a flush. One, two, three, four, five. So that's a flush. They're all the same suit. We've got ace of spades, 2 of spades, 3 of hearts, 4 of hearts, 5 of diamonds. That's a straight. So a straight is 5 cards in order, right, that they're consecutive. Now, in some games, aces are low, in some games, aces are high, so you could have a straight that looked like 10, jack, queen, king, ace, depending on the rules. But what you can't have is a straight that wraps around. You can't have something like jack, queen, king, ace, 2. That's not a straight. Okay? This doesn't work. You can have a straight flush. Okay, that's all 5 cards in a row, all the same suit. And then you can have a royal flush, which is 10 spades, jack of spades, queen of spades, king of spades, ace of spades. Okay? A royal flush is not a straight flush. A royal flush beats a straight flush. All right? Have I left anything out? Let's figure them all out. Okay, there's 52 cards in all, right? So when I'm dealing you 5 cards, there's 52 possibilities for the first, 52 possibilities, 51 possibilities for the second, etc. But in the kind of game we're talking about, you get your 5 cards, and what matters is what 5 cards you got, not what order you received them in. Doesn't matter what order they were dealt in. Okay? So how many hands of 5 cards are there from this 52 card deck? Okay, we have some votes. The number 52 factorial came out. What is 52 factorial related to? I mean, it's something to do with the deck of cards. It's the number of ways there are of putting all 52 cards in some order. It's basically the number of different ways the cards can be shuffled. If you shuffle the whole deck, how many different orders can the deck be in? All right? Okay, what would 52p5 be? Number of permutations of 52 things taken 5 at a time. Okay, so that's sort of the number of orders in which you can be dealt 5 of the 52 cards, if it mattered what order you got them in. Okay? If order doesn't matter, if all that matters is which 5 cards you got, and not whether you got the king first or the ace first, then the number of ways there are, the number of subsets of 5 of 52 cards is 52 choose 5. Right? Okay, very big number, nonetheless. All right. Let's see if we can, let's start by counting the number of ways there are of getting king high. Now, what makes card hands interesting and illustrative, why it's a good thing to look at is the strategies for figuring out how many ways there are of getting these different kinds of hands are different. The same strategy doesn't generally work for different hands. You've got to figure them out. So this illustrates different strategies for counting and illustrates that when you get a problem, you got to figure out how to solve the problem, not just look it up in the book, right? All right. So here, how many ways are there of getting, let's say, a king high hand for the sake of argument? What has to happen for our hand to be king high? Got to get a king, right? Okay. So how many ways are there of getting a king? 4. Okay, so we've got to get 4 ways to get it. There's 4 ways to get a king. Now, what else do we need to get? Okay, everything lower than a king. We need 4 more cards. Those cards have to be lower than a king. Let's call aces high for the sake of this. So we need 4 cards that are not kings or aces. Sorry? They can't be the same. I can't get 2 4s, for example, right? And they also can't be consecutive leading up to the king, or I'd have a straight, right? I can't have 9, 10, jack, queen, king, or that would be a straight. And they can't all be the same suit, or I'd have a flush. Okay, so we got to figure out a way of making decisions that produce a king high hand without producing a hand that's higher. Now, the strategy for this particular kind of hand is going to be, let's count things that count extra stuff we don't want and then subtract off the extra stuff. That's going to turn out to be the easiest strategy for this hand. This is one of the hardest. Well, there's some conceptual difficulties on the others. This is one of the hardest. All right, so we've got 4 choices for the king. And now we need to eliminate the kings and eliminate the aces and pick 4 of the remaining 11. There's 11 kinds of cards left. If we pick 4 distinct kinds of cards from the remaining 11, we've avoided getting a pair, or 3 of a kind, or 4 of a kind, right? Because we're asking for 4 distinct kinds out of the 11. That's eliminated getting multiples, yes? So if we take 4 times 11, choose 4, we've now specified which of the 4 kings we've got and which 4 of the remaining kinds of cards we get. But the problem is 11 choose 4 includes 9, 10, jack, queen, king. It includes 9, 10, jack, queen. And if we got 9, 10, jack, queen and have the king, we'd have a straight, not a king high. So this number, 11 choose 4, has counted some extra stuff we don't want. How much extra stuff has it counted? There's 13. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king is 13. We don't want to get aces and we don't want to get kings. Right? If we get an ace, we have an ace high instead of a king high. If we get a king, we have a pair of kings. So there's 11 different kinds left that we can pick from without blowing it and getting a better hand. Okay, we're talking about kinds of cards here. So it's okay to get ace, 2, 3, 4. It's okay to get 2, 3, 4, 5. It's okay to get ace, 5, 7, 9. It's just not okay to get 9, 10, jack, queen. There's only one of the 11 choose 4 possibilities that doesn't work for us because it gives us a straight. So we need to subtract 1. Okay, but we're not done because all we've specified here are what kinds of cards we got, not what suits we got. Okay. Why 1? Because I want all ways there are of picking 4 cards from 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, but not the one of those that corresponds to 9, 10, jack, queen. So it's all of them except that one, which would then give us a straight. Okay. All right. Regretting slightly doing this. Okay, so now we have one. Well, having done this way, let's do it this way. Instead of 4 kings, let's just say we're picking the faces of the cards first. So there's one thing. We're picking king. And now let's worry about the suits of all of the cards. Okay, so we now have 5 cards in our hand. We have a king. We have 4 cards that are chosen from 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, but not 9, 10, jack, queen. Okay, and now we need to assign suits to those 5 cards. How many ways are there of doing that? I get 4 choices for the king, 4 choices for the second card, 4 choices for the third, etc. 4 choices for each of all 5 cards. That's 4 to the 5th. Right? 4 times 4 times 4 times 4 times 4. But some of these don't work because some of those have all cards having the same suit, in which case I'd have a flush, which would be a king high. So how many of these 4 to the 5th ways of picking the suits correspond to flushes? 4, right? There's all 5 cards are hearts, all 5 cards are diamonds, all 5 cards are spades, or all 5 cards are clubs. There's 4 possibilities. Okay. Are we done? With this one? we multiply, right? We have one choice of kind of card for the king, essentially no choice. We got to get a king. Then we've got to pick the other 4 kinds of cards we have, but we need to pick them in such a way that we don't end up with a pair of kings or an ace. Okay, so this picks 4 distinct kinds of cards from the 11 remaining ones. This avoids getting a pair, 3 of a kind, something like that. Avoids getting an ace, avoids getting another king. But it accidentally included 9, 10, jack, queen. So we subtract that one off because that would have given us a straight. And then we now know which 5 kinds of cards we have. We need to figure out which suits we have for those 5 cards. There's 4 ways of assigning a suit to each of those 5 cards. That's 4 to the 5th. But that entire set, 4 to the 5th, includes the flushes. And we want to subtract off the flushes because we don't want to count a flush because a flush is a better hand. So there's 4 ways of assigning suits to the 5 cards that correspond to flushes. Namely, all 5 cards are spades, all 5 cards are diamonds, all 5 cards are hearts, or all 5 cards are clubs. That's 4. Okay? All right. So that's the number of king-high hands. What if we had changed this, instead of being king-high, we had made it be 9-high, for the sake of argument? What would change? Yeah, the 11 is what would change, right? Because we would have a 9. And then from the, how many cards are less than a 9? Aces count high. So 7, right? From the 7, we need to pick 4, but we need to avoid a straight, so we'd still be subtracting 1. Those things that are consecutively lead up to the 9, etc.
Wait, wouldn't there be more ways to make a straight with a 9 then?
If we're avoiding all the cards that are above the 9, by only choosing from the remaining ones that are lower, then it's still the, yeah. Okay, so far so good? All right, that's probably the hardest one of all of these. There's one that's got a little conceptual thing. There's a subtle difference between 2 pair and a full house, which we'll get to momentarily. But all right, how about 1 pair? What do we need to do? So this is not a pair of kings, but a pair, period. But we need to figure out what kind of card we're going to have a pair of. Yes? So from the 13 kinds of cards there are in the deck, we need to pick which kind of card we're going to get a pair of. Is it going to be a pair of kings, a pair of 2s, a pair of 7s, a pair of whats? Okay? So there are 13 choose 1 ways of picking which kind we're going to get a pair of. And then, what else do we need to do to end up with a hand that has exactly 1 pair and nothing better than that? Yes?
So that 13 choose 1 is choosing 2 cards for.
It's saying that the pair is going to be kings. Okay? There's more to do. I need to figure out which 2 kings those are going to be, right? So having said kings of the 13 kinds, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, I've picked king. There's 13 ways. I could have picked 7s. I could have picked 5s, whatever. This is saying there's 13 ways of doing that. 13 choose 1 is 13. Remember, n choose 1 is n. Having decided that the pair is going to be a pair of kings, I still need to decide which 2 of the 4 kings I'm looking at, right? How many ways are there of doing that? How many kings in all? 4. How many do I need? 2. 4 choose 2, okay. Okay, now I know what my kings, now I know that the kings are, for example, the king of diamonds and the king of spades. Okay, now what do I have to do? I got to pick these other cards. Yep. What are the constraints? What am I not allowed to do? What do I have to do? An ace would be okay. 2 aces would not be okay.
Or 3 aces.
3 aces would not be okay. I need 3 distinct cards, right? How many 3 distinct kinds of cards? How many kinds of cards am I allowed to pick from at this point? Okay, can't have a king. Anything else is okay, right? There's 12 kinds that I can pick from. Any 3 of those are okay, as long as they're all different. So from the remaining 12 kinds of cards, I need 3. So having picked, for example, 2s, 4s, and 5s, I still need to say which 2, which 4, and which 5. Yes? So for each of those, there's 4 choose 1 ways of picking a 2, 4 choose 1 ways of picking a 4, 4 choose 1 ways of picking a 5. That is, I get to pick either the diamonds, spades, hearts, or clubs, either the diamonds, spades, hearts, or clubs, et cetera, right? One of the 4 suits. So this is going to be times 4 choose 1 times 4 choose 1 times 4 choose 1, which is 4 times 4 times 4, which is 4 cubed, right? So all right, this kind of makes sense. We've decided that the pair is going to be a pair of kings. We've figured out which 2 kings those are. We've picked 3 different kinds of cards from the deck. Because these are 3 different kinds from the 12, we've automatically excluded the possibility of getting an extra king or getting a pair of anything else or anything more than that, because these are 3 different kinds chosen from the ones that remain after the kings are gone. Okay? So we've avoided anything better. And now we need to pick the suits for those 3. There's 4 cubed ways of doing that. Okay. After doing a pair, 3 of a kind and 4 of a kind should be really easy. So what do we get for 3 of a kind? Again, we got to pick what are we going to have 3 of. Okay, there's 13. Choose 1 equals 13 ways of doing that. Having picked the kind we're going to get 3 of, we need to pick which 3 we get. There's 4 choose 3 ways of doing that. There's 4 of them in all. We need 3 of them. 4 choose 3 is picking 3 to keep is the same as picking 1 not to get. Okay, so there's 4 ways of doing that. Okay, then we have 12 kinds left in the deck. We need to get 2 kinds that are not kings. Right, so from the 12 that remain, because we're excluding the kings, we need 2. And then, having gotten those 2 different kinds, we need to assign suits to them. We need to figure out which of the 4 cards of each of those 2 kinds we get. And that's 4 times 4's 4 squared. Okay? So again, very similar reasoning for these 2 kinds of hands. What kind do we get 3 of? Which 3 do we get? We need 2 other kinds so that we don't end up with 4 kings or something like that, and we don't end up with 2 pair, we don't end up with whatever, so we're picking 2 distinct kinds from the remaining 12, and then assigning suits to those 2 cards that we got. Question?
Yeah, what does it mean to assign suits now when it doesn't matter because you can't get a flush because you have 3 of a kind?
Well, so you could have gotten, here's one 3 of a, so the question is, why do you care about the suits if you automatically can't get a flush? And it's because we're counting all the different hands there are that are 3 of a kind. So this is a different 3 of a kind. And this is a different 3 of a kind. So we need to count all the different ways there are of doing it. We're not trying to rule out any possibilities. We're trying to count all the possibilities. All right, 4 of a kind now ought to be really easy. Somebody want to get me started? Do I have any choice for what the suits of those kings are going to be? No. I got to get all 4. There's only one way of doing that. Put in a 1, but it's not going to change anything. Then, from the remaining 12, yeah, 4 possibilities for the suit of that 1 card. All right. Okay, now it's going to get interesting again. Full house. Actually, let's do 1 pair first and then come back to a full house. Let me start 2 pair first and we'll come back to a full house. All right. What do I need to do to specify 2 pair? I'm hearing 13 choose 2. Let's explain that, please.
Well, you have to figure out which 2 cards you're going to use for the pairs.
Okay, so you need to figure out which 2 kinds of cards you're going to have pairs of. But from the 13 kinds of cards in the deck, this particular 2-pair hand has kings and 2s. Okay, so from the 13 kinds, we're picking 2 of which to have pairs. Having picked those 2 kinds, I have 4 choose 2 ways of assigning suits to one of the pairs. No matter what I do for that pair, I have 4 choose 2 ways of assigning suits to the other pair, picking which 2 of those 4 cards I get. And then I still need 1 more card. How many are there I get to choose the kind from? 11. Okay, by choosing that 1 kind from the 11, I've avoided accidentally getting 3 of one of those kinds. Right? I've ruled that out. Okay. Now, the crucial thing here to notice is that we did 13 choose 2, not 13 choose 1 times 12 choose 1. Okay, there's no difference between a pair of kings and a pair of 2s and a pair of 2s and a pair of kings. They play the same role in the hand, right? So if we did 13 choose 1 times 12 choose 1, it would be as if you could tell the difference between getting king of spades, king of hearts, 2 of clubs, 2 of spades, and getting 2 of clubs, 2 of spades, king of hearts. It's not any different. It's the same hand, right? Because the order in which you get them doesn't matter. They play the pairs play the same role in the hand, so we're picking 2 different kinds. They're exactly equivalent. So those 2 kinds that we get pairs of. That's why we got 13 choose 2 here. Okay, having done that, let's go look at full house. 13 choose 2? Okay, so this is exactly the issue, right? 3 kings and a pair of 2s is a different hand from 3 2s and a pair of kings. So they really do play a different role. Unlike this hand where the 2s and the kings play the same role. Okay? So I need to pick which kind of card I'm going to get 3 of, and then from the remaining kinds there are, I need to pick which kind I'm going to get a pair of. That makes sense? So I've got 13 choose 1 ways of picking which one I get 3 of, times from those 4 cards I need to pick 3. 4 choose 3 is 4. I'm just going to write down the 4. And then from the remaining 12 cards in the deck, 12 kinds of cards in the deck, I need to pick 1 of which to have a pair. And then 4 choose 2. Oh dear. Where am I going to put this? Well, it's 4 choose 2, which is 6. So from the 4 2s in the deck, I need to pick 2. All right, so the conceptual difference between the full house and the 2 pair has to do with the fact that in the full house, these cards play different roles because one you get 3 of, the other get 2 of. Whereas in 2 pair, these kinds of cards play the same role. You get a pair of both of them. You can't tell a pair of 1, a pair of kings and a pair of 2s from a pair of 2s and a pair of kings. It's the same. All right. Flushes. How many flushes? On to a different strategy. From the 13 cards there are in the deck, I need to pick 5 different kinds. They all need to be of the same suit. But what do I need to avoid? Straights, right? How do I figure out how many? So basically, if I took 13 choose 5, that's all the ways there are of picking 5 different kinds of cards from the 13, but that's going to include a bunch of straights. Because that includes ace 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, etc. How many of those are there? How many straights sort of are there that I've included? This is too big. We're going to use the strategy of count more than you want, subtract off the extras. That's what we're doing. So 13 choose 5 minus. Let's have aces count both high and low. So then you have ace 2, 3, 4, 5 is a straight, 2, 3, 4, 5, 6 is a straight, 10, jack, queen, king, ace is a straight. So you have straights that start with an ace, straights that start with a 2, with a 3, with a 4, with a 5, on up to starting with a 10. How many does that make? 10. Yeah, okay. Right? Minus 10. Okay. So we've eliminated the straights. And now what's left to do? Pick the suits of pick the suits of those 5 cards. Is it going to be 4 to the 5th? Blah, 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 blah? It's just 4, right? They all have to be the same. They can all be spades, or they can all be hearts, or they can all be diamonds, or they can all be clubs. Anything else, we don't have a flush. So this is just this times 4. Okay. How about straights? Well, we just did a big piece of this when we counted that, right? So there are 10 ways of sort of specifying what kinds of cards are going to be in a straight. Right? Because you can have a straight that starts on an ace, straight that starts on a 2. You get to pick the starting card. If you pick the starting card, the rest of them are already determined. And there's only 10 starting cards you can pick, ace through 10. Right? So we've got 10 ways of picking what kinds of cards are going to be there. And now we need to pick the suits of those cards. How many ways are there of doing that? He opens a parenthesis, indicating it's going to be complicated, but not that complicated. Yeah. There's 4 to the 5th ways of assigning, of picking one of the 4 of each of those 10 kinds of cards, but that's included straight flushes, which we don't want to include, -4. Because in the 4 to the 5th, we've counted all 5 cards are spades, all 5 cards are diamonds, all 5 cards are clubs, etc. So there's 4 if we want to get rid of. How about a straight flush? Okay, are there 10 starting cards? It's only 9, right? Because if we had 10 Jack Queen King Ace, that would be this. It'd be a royal flush. 10 Jack Queen King Ace of the same suit would be a better hand. So we've got 9 choices for the starting card, and 4 choices for the suit because they've all got to be the same: spades, hearts, diamonds, or clubs. Okay. What about a royal flush? The only thing you get to pick is what suit those 5 cards are. Okay, so this is the best hand because there's the fewest ways of getting it. Okay? All right, we'll put this back together next time. So won't see you guys Thursday, but see you next Tuesday.